Alright guys, so here's our first problem for momentum. We've got a 120 kilogram man standing on a 400 kilogram cart. They're moving together at a velocity of about 20 meters per second. The man jumps off the cart and hits the ground going in the opposite direction at about 12 meters per second. We want to know the velocity of the cart after the man jumps off, and we also want to know if it keeps moving in the same direction or not. So here's our initial setup. Man and cart moving at 20 meters per second to the right. Alright, here's the setup after. Man going to the left at 120, cart going to the right at some unknown velocity. This is going to be one of those momentum before equals momentum after problems. So we take the masses of the man and the cart, multiply them by 20, that's the momentum before, and we set that equal to the momentum after. Man's mass times man's velocity plus cart's mass times v. We then do the math. We try to solve it out. We're going to need to do some algebra by adding that negative 1440 to both sides. Then we're going to need to divide both sides by 400 kilograms. And once we do that, that should give us the velocity. And when we solve it out, we ended up with a velocity of 29.6 meters per second. Now notice that velocity is positive. And what that should tell you is that the cart continues to move in exactly the same direction that it was going before. It continues to move in the positive direction. Hope that one helps. Alright guys, so here's problem 2. We've got a 5,000 kilogram truck moving at 30 meters per second. It collides with a car that's stationary, not moving, that has a mass of 2,000 kilograms. After the collision, the two vehicles move off as one mass. It's an inelastic collision. And we want to know what's the velocity of the mass after the collision. So here's our initial setup. 5,000 kilogram cart moving 30 meters per second. Stationary 2,000 kilogram cart. Here's after the collision. They're both moving off together, 5,000 plus 2,000, 7,000 kilograms total at some unknown velocity. We're trying to find that velocity. So to work the problem, we use conservation of momentum. We say 5,000 times 30, the momentum of the truck before the collision, plus 0, the momentum of the car before the collision. That's equal to the momentum after, which is 7,000 kilograms, the combined mass, times v. We multiply things out, 5,000 times 30 to get 150,000 kilogram meters per second. That's on the left, the before side. And we set that equal to the after side, which is 7,000 kilograms times the velocity. Finally, we divide both sides by 7,000 kilograms, and that gives us a velocity for the combined mass of 21. Again, that total velocity is 21.4 meters per second. Alright guys, so here is momentum problem 3. This one's different than the other ones. This one's going to be what we call an impulse momentum problem. We have a 0.05 kilogram baseball moving toward a bat at 20 meters per second. The bat and the ball touch. They're in contact for 0.005 seconds. And the ball leaves the bat at negative 30 meters per second. It's moving in the opposite direction. We want to know how much force is applied by the bat to the ball. Impulse momentum, F delta t is called impulse, the force and the time, and M delta v is called change in momentum. Let's first look at what we know. In this problem, we know the mass, we know the time, we know the initial velocity is 20, and the final velocity is negative 30. That gives us a change in velocity of negative 50. Think of it like it's on a number line. So we set up F delta t equals M delta v. Impulse equals change in momentum. Go ahead and divide both sides by t to solve for F. So that's going to give us 0.05 kilograms times negative 50 meters per second divided by 0.005 seconds. When we do the math on that and we solve it out, we end up with negative 500 newtons. But we need to write that with the correct number of significant digits, so negative 5.0 times 10 to the second newtons. And that negative sign tells us that the force is acting in the opposite direction of the original motion. Again, this is an impulse equals change in momentum problem.